Hi everyone. This presentation covers the new feature updates for the OCI Application Performance Monitoring Service as of May 2024. My name is Yutaka Takatsu, one of the product managers in the OCI Observability and Management product management team. Although this update is for May 2024, it includes features released in the past few months. For more details on the release timings, please refer to our release notes page. Here is a list of new features I would like to introduce in this recording. With span enrichment, you can drastically enhance spans. You can add custom attributes or edit existing ones, making them more meaningful when analyzing your application. We also released the OpenTelemetry operator for Kubernetes, which automatically injects the APM Java agent into your Kubernetes cluster. While we already have a few methods to achieve this, this feature offers a quicker and easier way to deploy that Java agent in a Kubernetes environment. There are a couple of enhancements in the trace query language, or TQL. The nested query feature allows you to construct complex queries using subquery functionality in TQL. You can use the result of one query to retrieve information in another query. Cluster by command in TQL allows you to create clusters from the traces and identify outliers. You can display the result in a grid view or a bubble chart widget in the dashboard. The new Trace Data Widget Builder allows you to transfer trace queries by copying and pasting them from the Trace Explorer UI to the dashboard creation page. This makes creating dashboards much easier and more intuitive. Threat Activity Monitoring, which is integrated with the OCI Threat Intelligence Service, allows you to monitor potentially malicious client activities in your applications. And how it works: when APM collects client IP addresses from user activities, it validates them against a threat intelligence database to check for matches with existing threat information. And there are three enhancements in the synthetic monitoring. On-premise Vantage Point, or OPVP, is a new type of Vantage Point. It is designed to be deployed on any location, either on your on-premise data center or other cloud vendors, and securely runs your synthetic monitors within your secured networks. The Synthetic DNS Monitor is a new synthetic monitor type to test the availability of DNS servers. And lastly, Network Data Explorer. This is a topology diagram that visualizes the end-to-end network data path for your synthetic monitor runs and allows you to run analytics on the latency and packet loss by comparing the different setups. Let's kick this off with a span enrichment. By default, APM captures many valuable metrics and dimensions essential for your trace analysis. You can see them in the Attributes pane in the Trace Explorer and use them for filtering or drilling down your data. In addition to these out-of-the-box attributes, your application generates a lot of distinct data points that the APM agent collects. The span enrichment feature surfaces these application-specific nuances, allows you to create custom attributes out of it, and integrates them directly into the spans. This capability not only enriches your trace data, but also streamlines the analytics process. Please look at the diagram on the screen. Your application runs on the top. The data is collected from various application components, such as browsers and servers, and goes into the pipeline. However, the data may not be formatted in a way that is directly useful for your data analysis. For example, error code 401 may not be intuitive for many users. Now with the span enrichment, we can take this data and add it back to the pipeline as custom attributes. For example, URLs can be converted into functional or business names. IDs can be converted into customer names or departments. Error codes can be mapped with more meaningful error description. And this can be done by uploading map file to the APM domain. If you have a CSV file that compares two values, error code and error description, you can feed the data into the span enrichment feature so that the description can be used as an attribute value instead of an error code. That was a high-level introduction to the span enrichment feature. Now let's look into more detail with examples. There are two types of span rules, out-of-the-box rules and custom rules. Out-of-the-box rules are provided by Oracle and can be used as is because they are already pre-configured for common use cases. So for example, you can use the out-of-the-box rule that copies the IP address from the client from which the span was generated, transfer it into the span, and show the value as an attribute. The diagram shows the configuration. First, you will define the span filter. This is a condition of the query in trace query language. In this example, the filter pattern is component equals to browser. Next, create a rule group and specify the span filter name defined in the first step. Finally, create a span rule within the group. In this case, we selected an Oracle-provided span rule, which adds the client IP address to the span. The right-hand side of the screen shows the span details view before the rule was applied. Once the rule is saved, wait for some time for a few transactions to run, and the data gets populated. Soon you will see an attribute added to the span, which is called client IP, with a client IP address as a value. You can also create your custom rules to solve a variety of problems. For example, as we mentioned in the previous slide, you can configure the rule to show a meaningful error message in the attribute instead of an error ID by looking up a mapping file which has a list of error IDs and error messages. Next, let's take a look at the structure of the span enrichment rules. First, define a query that filters spans. For example, components equals to browser. The span rule will apply to all the spans with this condition. Span enrichment is configured through the span rules, and the span rules are managed within a group. Span rules contain one or more rule actions, and multiple span rules can be configured in a group. Once configured, the rules apply to the spans with a defined query condition. The rules will be applied in a particular order defined in the group. Also, multiple groups can be defined to match the same span. And if a span matches more than one group, the order is determined by the priorities set by each group. Span rules can be defined using different types of actions depending on the use cases. The actions types are generic, numeric, string, and pass-through. Let's see some examples for each of them. You can use generic action to map existing attribute values to new values. You can also remove a value from an existing attribute, rename the attribute, or create a new attribute. For example, an existing attribute collects values 1, 2, or 3. You can map the attribute values to blue, red, and green respectively by uploading a mapping file. Another example, an existing attribute is collecting PII information. You can use generic action to remove the particular attribute from the pipeline. Numeric actions enable applying mathematical functions to the data. For example, convert a unit from seconds to milliseconds, or bucketize a value range and map it into the specific bucket values such as cold, warm, or hot. With string actions, you can modify the string attribute values. For example, combine values from multiple attributes, or extract a portion of a longer value and create a new attribute. And lastly, using pass-through actions, you can define a query condition and block certain spans or add sampling to the data. For example, add a 10% sampling to the total browser spans to reduce the traffic coming into the pipeline. Let's look at some more examples with actual configurations. This example defines a span rule that uses a string action to extract the first word from the SQL and creates a new attribute in the span. First step is to define a span filter. In this example, the pattern is DB statement is not omitted, so it applies to the JDBC calls. Next is to set the span group name and select the span filter name configured in the first step. Within that group, create a span rule. Set the rule name and definition of the rule. Then create an action. Here, a string action is used to extract a string based on the regular expression pattern. The name of the output attribute is SQL category. This will extract the first word of the SQL statement and create a custom attribute. You can use this attribute to filter or categorize the JDBC span to enhance your trace analysis experience. The attribute also appears in the span details view with the attribute name SQL category. Another example. This time, the generic action is used to map the values of an existing attribute to the values from the file and create a new attribute. First step is to define a span filter. In this example, the pattern is component equals to browser. Next, set the span group name and select the span filter name configured in the first step. Within the group, create a span rule. Set the rule name and definition to the rule. Then create an action. In this example, the map attribute rule action is used. It allows you to upload a text file that has two columns of username and the user's corresponding department. The rule will create a new attribute, department, and add it to the span. The attribute appears in the span details view and also can be used in the Trace Explorer to filter and query the data. Pass-through actions also provide a valuable option for your tracing analysis. You can remove or reduce the volume of specific spans. Note that in this example, a span filter is not defined. Instead, the pattern is set directly in the group. Then create a span rule to sample the browser spans. Next, create an action. Select the span entry, then pass-through actions and select sample. Finally, set the percentage of the sampling. This will reduce the volume of the spans. This can be useful when you see a lot of very fast spans that are not important for analysis. It also reduces the total cost of the monitoring. The next feature I would like to mention is the Open Telemetry operator, which we customize to automatically inject Java agents in Kubernetes. OCI APM supports Java applications that run on Kubernetes, and there are already a few methods to deploy an APM Java agent in Kubernetes pods. One way is to build a Java agent pre-deployed into the pods. Or you can configure it using the shared disk space, which can be done without involving the development. In the recent release of OCI APM Java agent, now we support an alternative and easier way to deploy the Java agent in Kubernetes by utilizing the Open Telemetry operator for Kubernetes. You need to create and edit the Kubernetes custom resource definition, or CRD file, to point to the Java agent location and configure it with APM data point and data keys. Once this one-time operation is completed, when a pod is restarted or a new pod is generated, OpenTelemetry operator detects the event and triggers the auto-injection of the APM Java agent to the new pod. And this will done automatically to all the JVMs running on newly created Kubernetes pods. There are 3 steps to set up an OpenTelemetry operator to automatically inject the APM Java agent. The first step is to install the Cert Manager and OpenTelemetry operator into the Kubernetes cluster. They can be downloaded and installed from the GitHub links shown on the screen. And please note that you need Cert Manager pre-installed before installing the OpenTelemetry operator. The second step is to configure a CRD file with information to deploy the OCI APM Java agent. The endpoint that locates the Java agent installation has to be specified. APM domain information, as in APM data endpoint and data key, need to be entered too. The third step is to add an annotation to the namespace to tell the cluster for which pods the APM Java agent should be automatically injected. The annotation can be added to an entire namespace or specific resources such as in pods or stateful sets. Here in this example, an annotation was added to a namespace. Once these steps are completed, a Java application that runs on all pods within the namespace will be automatically instrumented. And please refer to the blog with the link shown on the screen for more details. We also have a few enhancements in the trace query language or TQL. Now we support the nested query functionality in the language. A nested query uses the result of one query to refine another query. The example on the screen shows a query that retrieves a list of traces which their backend is invoked in a specific Kubernetes namespace. Taking a closer look, I can see a show spans statement that is nested within a show traces statement. This query uses the result of the inner query to retrieve the result of the outer query. First, it looks for the trace IDs of the spans where the Kubernetes namespace is prod A. Next, it takes the result of the inner query and shows the trace information accordingly. You can also replace the condition in where clause and retrieve a different set of results based on your use case. In the second example, the query retrieves all traces which invoked the database transaction with an insert statement. The third example shows the average session duration by country. It calculates the session duration time dynamically in the inner query and uses that information to extract the result in the outer query. Another TQL enhancement we have is a clustering. Now in the APM Trace Explorer, you can use the trace query language to create clusters from the traces and the spans, identify the outliers, and show the results in a grid view or a bubble chart widget in the APM dashboard. To use this functionality, utilize the cluster by command, which supports numeric metrics and string dimensions. Once the command is executed, results will be shown with columns as in the outlier, percentage, and the attribute values. The syntax is straightforward. Begin with the query statement with the cluster by command and place single or multiple attributes which you want to create clusters against. The clusters can be also created from a query with a specific condition in a where clause. The screenshot at the right shows a table view when the cluster by command was executed with a query showing spans with values of the span duration metric. The query created a cluster based on the range of the values, added count and percentage to each cluster, and measured an outlier out of them. In addition to the table view, you can also visualize the cluster data in a bubble chart in the APM dashboards. The Microservices Overview dashboard has an out-of-the-box widget which represents the top server request of the selected APM domain. In the chart, clusters are displayed in a bubble object with different sizes. Big objects are known outliers that compose a majority of the query results. Small objects with red indicates, however, are the outliers that may require attention. By clicking each object, it drills down to open the Trace Explorer with contextual query results in the table view so that you can run further analysis on it. In addition to the out-of-the-box bubble chart, you can create your customized clustering chart using a query you found useful in Trace Explorer. We will cover that in the next Widget Builder section. With the new Trace Data Widget Builder, APM dashboard creation is easier than ever. With this feature, you can transfer trace queries by copying and pasting from the Trace Explorer UI to the dashboard creation page. That's it. By saving the widget with a few additional configurations, your custom APM dashboard is ready within minutes. For how this works at a high level, first, Find a meaningful query in Trace Explorer that you want to use as a source of your widget. Second, create a new dashboard or edit an existing dashboard and add a new query-based widget. And finally, select the visualization of your choice. So let's look at this with a little more detail. To create a dashboard using the Trace Data Widget Builder, first go to the dashboard page and create a new dashboard. You can also add the widget to an existing dashboard. With a dashboard in editing mode, from the Widgets tab, select Add Widgets, then select the Create Query-based widget. Once the page is updated, select Traces as a data source. That will open a query view in the right side where you can enter the query, which you can transfer from the Trace Explorer. Press the Run button on the right-hand side. This will populate the data in a table view. You can also change the visualization. So for example, to create a custom cluster by widget similar to what we saw in the previous slide, select the bubble chart as a chart type. You can also select other chart types such as line chart, bar chart, or pie chart. Another powerful feature we have introduced in the security area is threat activity monitoring. APM can now monitor client activities that are potentially malicious to your applications. Threat activity monitoring is integrated with the OCI Threat Intelligence Service, which has a database of suspected IP addresses collected from various sources. Every time APM collects client IPs, it checks this database and validates them against a list of suspected IPs. When your application is accessed by an IP listed in the Threat Intelligence Service database, APM automatically flags the transactions by that user. You can visualize such data in the out-of-the-box dashboard, set an alarm to receive notifications, and drill down to the traces to investigate. In the span details view, you will see a few threat-specific attributes which you can use for the analysis are added to the span. APM has an out-of-the-box dashboard for threat activity monitoring. When there is a detection of potentially harmful client access, the transaction data populates into the dashboard. Looking at the bottom, you can see the list of IPs that are flagged as a threat, their volume of transactions, their threat types, which are defined by the Threat Intelligence Service, and their origin of the access. In the Services widget, you can see what services are invoked, whether that was only at the login service, where such a user should be blocked and no further harm was done, or it was other business services that indicated the user came deeper into the system. You can also see what SQLs are executed by those transactions and measure the severity by checking whether it was a harmless query or a more critical one, such as retrieving customers' private information. So to summarize the benefits, when a potentially malicious user accesses your application, APM validates the IP with the OCI Threat Intelligence Service, visualizes the transactions in the dashboard, and alerts you with notifications, and allows you to go back the time and drill down to the detail to know what activities were done by those users. For more details, please refer to the blog with the link shown on the screen. As for the area of synthetic monitoring, recently we released On-Premise Vantage Point, or OPVP, which is a new type of vantage point that can be deployed in any location, whether that is on-premise or in other public cloud environments. This is a new addition to the existing vantage point options we already have. Let me recap on their benefits and compare the difference among them. First of all, we have public synthetic vantage points. These vantage points are located around the world, so if your application has publicly accessible endpoints, you can take advantage of the pre-configured public vantage points to test your application from global locations. If your application runs in OCI network, but cannot be accessed by public synthetic vantage points, you can set up dedicated vantage points within your OCI tenancy and have complete control over your network settings. However, the dedicated vantage point cannot be used if your application is not accessible from the OCI network. That is why we have the third option. And what we have now is the improved version of the dedicated vantage points. You can deploy the released OPVP anywhere, such as your on-premise locations or another secured cloud environment, and monitor your application's private endpoints. To deploy the released OPVP, you can follow the 3-step Get Started guide on the OPVP page. The first step is to set up dynamic groups and policies that are required for OPVP to communicate with OCI. The second is to download synthetic worker images that are needed for running monitors in your OPVP. Once these are done, you can look at the worker usage instruction page to create a startup script to run worker on either Docker or Kubernetes cluster. Synthetic DNS Monitor is a new monitor type available in synthetic monitoring. You can use the DNS Monitor to test the availability of DNS servers and their delegations to the collect authoritative servers for multiple DNS records. 3 types of configurations are available. First is a DNS server, which runs queries against the DNS server and measures the resolution time and availability. Second is a DNS trace, which validates a DNS request whether they are correctly dedicated to the authoritative servers in the child zone from the parent zone. The third is the DNSSEC, which validates the authenticity of DNS records according to the domain name system security extensions. It provides a data view for the DNSSEC trust tree and a data chain and measures the resolution time and availability. With Synthetic Network Data Explorer, you can visualize the end-to-end network data path of your synthetic monitor runs in a topology diagram and analyze the latency and the packet loss by comparing the data path of the monitor runs from different vantage points. To access the Synthetic Network Data Explorer, go to the History view in the Synthetic Monitor page, open the menu and select Network Data Explorer. This will open a Network Data Explorer page with the data paths of the selected monitor runs. In this example, monitor runs from 3 different vantage points are displayed. The data path is connected with the dots and lines. Each dot represents an IP address of a router that was pinged by the probe packet. You can also highlight the IP nodes and lines based on the link delay and packet loss threshold settings. In this example, link width is based on the packet response time, where delay time with more than 100 milliseconds shows in the red dotted line. Hovering the mouse cursor on the IP nodes shows the details of the router, such as IP address, packet loss value in percentage, and the location of the router. You can also hover on the connection line that shows an average packet response time. This is the end of the recording of the new feature updates for OCI APM May 2024. Thank you for watching.